70%, it will react by the 28 days, and it is usually present about 40 to 70% within the cement, this allied component. However, talking about the belite component, which is responsible for the later age strength, this later age strength, it will give you the strength about 6 months, 1 year. It will give the reaction about 30% at 28 days. But however, this 70% reaction will complete in the later ages actually. So it is present about 20 to 40% in the cement. These are the two main constituents of the cement, CaO and SiO2. So remember, these are two calcium and silicon dioxide. They make it actually C3S and C2S. Tricalcium aluminate. This is the third compound or third constituent, major constituents of the cement. It is actually development. It is used for the early stiffening or generate high heat of hydration. High amount of C3A. It means that you have early stiffening of the cement. It will increase the early setting time. And if you have high C3A within the cement, it cannot be used as a resistance to sulfate attacks. However, it generates a lot of heat of hydration. So we call it as high alumina as well, which is not written over here, but it will give very less, even we say negligible amount of, you can say, contribution towards the strength. So this content actually, which is responsible for early stiffening, we add gypsum into the system so that it can control early hydration. So by adding the gypsum, we can end two problems. One is flash set, another one is fall set. Flash set is means no gypsum. Flash set means, gentlemen, you put the water into the cement. What happens? Cement generally, within no time, it make itself stiff. And if you try to remix it, it will change its characteristics. So this flash set is never desirable. However, talking about the fall set means it is something like a thixotropic behavior of clay, that you add too much of the gypsum, suddenly cement make itself stiff. So as soon as you further stir it or further you again mix it, it will go into the fluid state. So these both characteristics are not desirable in the cement. So once we add too much gypsum or once we add very less gypsum, these both are not desirable. Are we clear?
Yes, sir.
Okay. So move to the next one. The fourth constituent, that is tetraaluminoferrite. This governs with basically about the color of the cement. It is present with between 1 to 4 or 1 to 10% written over here. Most of the books write it about 1 to 4%. So sometimes you have iron oxide, you have aluminum oxide. So these compounds are there. This acts as a flux actually. So other compounds, they give very little contribution towards the strength. But these compounds, they can be controlled, they can be used to control or govern the color of the cement. So these four constituents are there. Then if we have oxides, let's say we go for the cement composition, we can have calcium oxide, we can have silicon oxide, we can have aluminium oxide, iron oxide. So we can find out the compound or quantity of the C3S, C2S, C3A or C4AF by simple Bogue's equation. This is mathematical equation through which we can find out the, you can say, compounds actual percentage available within the cement, the total mass of the cement actually, how much it is available. This is a simple method or general equation by the Bogues which can be used to find out the compounds. However, talking about their real percentage, if we want to determine that, how much is the real percentage of C3S, C2S, C3A, C4AF is real time available within the cement, we can find out and we have mixed the cement, and practically we want to experimentally find out how much is the cement content of these four constituents. There it is very difficult. Until now, only Canada has this facility to experimentally found out these four constituents after mixing with the water. So, but generally we do this by the boards. Cement hydration, gentlemen. Cement hydration, we have C3S, we add water into it. What happens? We get CSH, which is called as calcium silicate hydrate. Remember this equation. So plus one unstable compound of this calcium hydroxide. This calcium hydroxide further reacts with the water and it can have calcium and hydroxyline. So remember, as these two compounds, C3S and C2S, they are about 75% of the weight of the Portland cement. So they are responsible for the strength. This calcium silicate hydrate, CSH, is a compound which is responsible for the strength development. If we the main compound, stable compound, which is responsible for the strength, that is called as calcium silicate hydrate. However, this calcium hydroxide, CH, this is most unstable compound available within the cement. You have gone through the durability, isn't it, everyone?
Yes, sir.
So what is the compound which is causing the major durability related issues? Can anybody tell?
Sir, C3A.
Anyone else? Anyone else who can tell there which compound is there within the cement which is responsible for the durability related issues?
So when calcium silicate hydrate gel reacts with water, then it will swell and it will issue.
You are saying that calcium silicate hydrate, it will react with water. What are you saying? Is it?
Yes, sir, in presence of moisture, it will swell and it will cause, when it will expand, then it will cause durability issue.
Remember, students, please, you should remember this. This slide is visible to you.
Yes, sir.
Yes, sir.
This slide is visible to you for the cement hydration.
Sir, visible है.
Okay, so there are two compounds. One is calcium hydroxide, and
जी
another
सर,
one is
बिल्कुल
calcium
नजर आ रही.
hydrate. There are two compounds. One is calcium hydroxide, other one is calcium silicate hydrate. Is it? These two compounds are there. Are you seeing it, everyone? Everybody, is it visible to you that there are two compounds within the cement? After getting it reaction with the water, there are two compounds. One is calcium silicate hydrate, one is calcium hydroxide. Are you with me?
Yes, sir.
Yes, sir.
Okay. So this calcium hydroxide is the most unstable compound within the cement, which is causing the problem regarding the durability. Remember. So I don't know what durability you have studied, but this CSH, it represents about 50 to 60% of the volume of fully hydrated cement paste. Although we know that it is about hexagonal structure, polymerized, sometimes says it is amorphous, but still its structure is not well understood, this calcium silicate hydrate. But we say that it is porous. So this porosity is about 25, 28%. So still it has cohesion between the walls. So we see that this structure is more stable. So this fully hydrated cement paste cannot absorb more water, more any other kinds of compound. However, this Portlandite or this CaOH twice, this represents about 20 to 25% of the volume of fully hydrated cement paste. This morphology It can be affected by the temperature, impurities, or any other compound. So all the durability with respect to chemistry or chemical, that is related with this compound. Are we clear, beta?
Yes, sir.
So it means if we say that the most of the problems within the cement, they are, while once we get the hydration of the cement, most of the problems, they comes through this particular element that is called as CH. So we need to stabilize it. It is most unstable. So this has the, you can say, tendency to be affected by the temperature, to by the impurities. So once these two things comes and they react with this and they make any kind of expensive compounds. So we talk about its structure of the cement hydrated paste. It starts with the spine-like needle structures at 3 days. Then it goes to the honeycombing-like structures, and it further move into the CH like the structures of needles. So although it is also a weak link, it has very low strength or high porosity and high permeability. So if we go to the further, it will make like this solid structure if we see it. Then there are also unhydrated cement grains are there. Sulfoaluminate, calcium sulfoaluminate is also there, which is called as a tringites. So this calcium sulfoaluminate is actually due to the C3A. Once it reacts with the C3S. So we can find out with the water, we can have calcium sulfoaluminate. These tringites are actually, or some people say it as a tringites, they are mostly prismatic needles are there. They go into the into a hexagonal monosulfate plates. So if we see that, this is small tringite formations, needle-like structure that is there. And it is expensive one. Expensive mean it has more volume. So that's why we see that cement right at the start of this reaction, it has high volume. Later on it squeezed or it went down. So, but still this tringite is unstable one. It does not can take more load. So if we see that over here, so maximum we want from the cement that the C3CSH. So this CSH or calcium silicate hydrate, this will give us the most, you can say, stable structure for cement paste to be stable, to get the main strength or more durable. However, we have unstable CH, this will lead towards the instability or towards the durability related issues. I hope you have studied it in your durability, but if not, we'll discuss it inshallah. So this is regarding the chemistry of the cement, how these four constituents and what are the products we get out of the cement once it gets interacted with the water. So talking about the specifications, we can have 5 different types of cements. So number 1, type 2, type 3, type 4, and type 5. So one is ordinary Portland cement, then we have moderate sulfate cement, then we have high early strength cement, low heat of hydration, and high sulfate resistant cement. So these are 5 major types. Then we have further subdivision of these 5 types. So why we have these 5 types? These are required as per the conditions or their different performances. So we vary the chemical composition or physical characteristics, we can get different types. Just like if we want to have high early hydration cement or high early strength cement, we can go for the higher content of C3A and C3S. So we can have low heat of hydration, we can reduce the C3A. Sulfate resistance is there, we can reduce the sulfate content, which can react with the other sulfate volumes. So talking by controlling the chemical composition and physical characteristics, we can develop any kind of cement. Type 1 is the most commonly used cement which we used. Sulfate resistance is mostly under the soil we use. Only low heat of hydration is also an option. Then early strength means we want fast setting. Sometimes we need it in precast industry or high-rise buildings where we have cold weather. We can go for the high early strength cement or faster setting. Talk about the low heat of hydration. Do you want to ask something, Uzair?
नो सर, वो गलती से ऑन हो गया था लाइक।
Okay. So talking about low heat of hydration cement, we get delayed reaction. So it means if we have a mass concreting, something like in dams or in huge mass concreting, we can go for the low heat of hydration so that lesser heat will be evolved in response of this reaction with the water. High sulfate resistant cement mostly used in the once we have sewer lines or pipes or industrial exposures or sulfate soil. So we use this high sulfate resistant cement over there. Then one more type which is very commonly used in developing countries like us in Pakistan, India, that is called as blended cement. This blended cement is actually, we have raw materials like fly ash, slag, we have silica fume, calcinide clay. We blend it with the cement with a certain proportion, and we can have Portland blast furnace slag cement, Portland pozzolan cement, Portland modified Portland cement, slag modified cement. So these all are different kinds of cement. Those can be blended with any kind of raw material, which is a byproduct of any other thing. So we can use it. So what is the benefit of it? So we will reduce any kind of, you can say, lime or calcination, or we can use lesser CO2 emission. Byproduct we can use the raw solid waste, and we can also have improved concrete performance. This last word, which is called as improved concrete performance, we'll discuss it in a while, inshallah. But remember one thing, the critical guy within the cement, that is, there is actually CH. Okay. So how much is the cement production? This is about 2015 stats. You can have even higher amount of production of cements. You can have its percentage of area of production. You can have it. This stats can be varied now. If you, I'll see that these are very later or not latest one. You can go for this. So some are the special cements are there, white cements, or primarily used for the decoration part or architectural workers. Then water repellents are there. So water repellents means you use the cement that can repel the water and they resist any kind of hydrostatic pressure. These are there. Then masonry units are there. You can use the mortar cement. Then to test the cement, we can have density test. We can have bulk density. Then chemical analysis of the cement, which can give us C3S, C2S, C3A, C4AF. These are ASTM C114 we can use to find out. Actually, it will not give us these four compounds directly. This test will give us CaO, calcium oxide, silicon dioxide, iron oxide, aluminium oxide. Through those oxides, using Borg equation, we can find out these four compounds. The direct composition we cannot find through this cement, this test, okay? Then fineness, we can use the Blaine fineness test, through which we can find out how much is the cement is there, particle size is there. Then most advanced technique right now, which is used to find out the particle size, that is called as laser diffraction particle analysis. See, in Pakistan, I think we have only one machine over here in Islamabad, in Nust, I think, or in Army Institute, where we can go for this test. So cement Blaine fineness is about 300 to 370 meters square per kilogram. This is the fineness we have. So remember, more finer is the cement, faster is the hydration, or more heat of hydration generation is there, or higher early strength is there. But long term, you may have problems. Early hydration, faster hydration, they will lead towards you the hydration process or shrinkage problems. So there are a lot of, you can say, problems with the fineness, but fineness can increase the rate of hydration. It can give you the early hydration. So then comes the initial set. Initial set is from 1 hour to 4 hours. You can write down as per the standard, it is 45 minutes to 4 hours actually. Final set time is 3 to 6 hours. It has gone up to 6 to 8 hours even also. Fall set and flash set, I have already given you the definitions in the previous phase. So fall set, if you remix it, so it can be remixed. But flash set cannot be remixed. You can remember it like that. Then setting time can be checked by the Vicat apparatus. You can use it. Then different setting times of the cement, heat of hydration you can find out. These are all different tests of the cement. On cement, you can perform the compressive strength test, which is normally done on a cube of 50 by 50 millimeter. So simple strength test can be there. Then air content meter is there. Then this flow table test. You can go for the flow table test. ASTM C1437 is there. So you can go by the how much cement can flow table. We find out the diameter of the flow. This is called as flow table. We put the cement within this truncated bucket and then we blow this table for 25 times. After blowing it 25 times, we find out the diameter of spread. There, how much is the diameter of spread? After seeing this spread diameter, we can find out the flow. Thermogravimetric analysis. These three tests are actually, we expose the cement to higher temperature and then we see there at which temperature the disintegration of different chemical compounds starts. So we increase the temperature, let's say C3S is gone, calcium oxide is gone. So these, how much is the mass loss? How much is the compound loss? So this is called as TGA or DTA. Then transportation of the cement is actually done in silos, big bunker silos, and so that it should be airtight. No water can or no moisture can penetrate into the cement. Then there are question and assignment. The gentlemen, you need to discuss different types of the cements available in Pakistan, their characteristics. Then you can submit in discussions in a group actually. So this ends our discussion with the cement. Right after 10 minutes, we'll start with our discussion with the supplementary cementitious. We'll have a break of about 5 to 10 minutes, then we'll start. I have 2:10, we'll start at 2:20. Are we okay?
Okay, sir.
So right after 10 minutes, we'll start with the supplementary cementitious materials.